We'll start into the basic understanding of electromagnetic radiation. We'll talk about what it is, covering different types of energy waves like radio waves, microwaves, infrared, visible light, UV, X-rays, and gamma rays. We'll highlight how it is everywhere around us and its crucial role in spectroscopy. Now, we'll break down the meaning of electromagnetic radiation into simpler terms. Electromagnetic radiation is a type of energy that travels through space. It's like invisible waves made up of electric and magnetic fields moving side to side. These waves have different lengths and frequencies. We'll discuss further how these waves work together and will highlight their importance in understanding spectroscopy. These are the wave properties that describe electromagnetic radiation, which includes wave height or amplitude. It tells us how strong or intense the wave is. A bigger amplitude means a powerful wave. Second is wavelength. It is how long or short the wave is. Short waves are like small ripples, and long waves are like big ripples. Third is frequency. It is how often the waves repeat. High frequency means waves come quickly, and low frequency means they take more time between each wave. Let's now proceed to electromagnetic spectrum. It includes everything from the slow, long waves like the radio waves to the fast, short waves like the gamma rays. It also includes the visible spectrum, which has wavelengths which ranges from 400 to 700 nanometers. So understanding the electromagnetic spectrum help us see how different types of wave interact with matter and it is and how it is crucial in the field of spectroscopy.
Here are the basic components of spectroscopic instrumentation: source of energy, wavelength selector, detector, and signal processor. All forms of spectroscopy requires an energy source. The specific type of energy source used depends on the spectral range of interest and the technique employed. This may vary from EM radiation, thermal radiation, and chemical sources. In absorption and scattering spectroscopy, the energy is supplied by photons. Emission and photoluminescence spectroscopy use thermal, radiant, or chemical energy to promote the analyte to a suitable excited state. EM sources can be further classified into continuum or line sources. The wavelength selector is used to isolate specific wavelengths or ranges of wavelengths from the incoming EM radiation. Ideally, it has a high throughput of radiation and a narrow effective bandwidth. It can be a filter, monochromator, or interferometer. Using filters is the simplest method for isolating a narrow band or radiation. They can be simple, such as colored glass or gel filters, or more complex interference filters that exploit the principle of interference to selectively transmit certain wavelengths. Monochromator is another method. Radiation from the source enters the monochromator through an entrance slit. A collimating mirror then collects radiation and reflects a parallel beam to a diffraction grating, where radiation is dispersed, while a second mirror concentrates it onto a planar surface that includes an exit slit. Interferometers exploit the interference of light waves to select specific wavelengths. Radiation from the source is focused on a beam splitter that reflects half of the radiation to a fixed mirror and transmits the other half to a movable mirror. The interference between the two beams produces an interference pattern that depends on the wavelength of light. The detector captures the radiation transmitted through or reflected from the sample. It converts this radiation into a measurable signal, typically electrical, which can then be processed and analyzed to obtain spectroscopic information. Ideally, it produces a signal that has a linear function of the electromagnetic radiation's power. Modern detectors use a sensitive transducer that can be a photon transducer or a thermal transducer. The table here shows examples of transducers for spectroscopy. A transducer's electrical signal is then sent to a signal processor. It displays the signal in a form that is more convenient to the analyst. Signal processors can be an analog or digital meters, recorders, and computers equipped with digital acquisition boards. It can also be used to calibrate the detector's response, amplify the transducer signal, remove noise by filtering, or mathematically transform the signal.
Absorbance and transmittance are two separate but parallel terms that describes the attenuation or the reduction of a light or electromagnetic radiation's intensity as it passes through a sample. Transmittance is defined as the ratio of the electromagnetic radiation's power exiting the sample, denoted by PT, to that incident on the sample from the source, denoted by P naught. Attenuation of radiation as it passes through a sample leads to a transmittance less than 1. And as shown in the equation does not distinguish the difference between ways on how the attenuation of radiation occurs. Besides absorption by the analyte, several additional phenomena and factors contribute to the net attenuation of radiation, which includes the reflection and absorption by the sample, absorption by components of the sample matrix or the solvent, and the scattering of radiation. And to compensate for this loss, uh, we use a method blank, and this method blank is used to uh, measure the radiation's power exiting from this blank that is taken to be the P naught or the incident. Multiplying the transmittance by 100 gives the percent transmittance, which varies between 100 and 0%. 100 meaning that there is no absorption, and 0% meaning that there is a complete absorption. All methods of detection, whether the human eye or a modern photoelectric transducer, measure the transmittance of electromagnetic radiation. Lastly, an alternative method for expressing the attenuation of electromagnetic radiation is called absorbance, or A, which is defined as A is equals to the negative log of transmittance, or negative log PT over P naught. And we can also transform this into another form, which is A, or absorbance, is equals to the log of P naught over PT. And absorbance is more common unit for expressing the attenuation of radiation, and this will be shown in the next sections or next lessons, since it is or it has a linear function that could lead us to the analyte's concentration.
And now we will talk about Beer-Lambert's law. So Beer-Lambert's law is a fundamental principle in chemistry, specifically used in the field of spectroscopy. So it helps us understand how light interacts with substances and how we can use that interaction to learn more about those substances. So now imagine you have a solution, a liquid, perhaps a colored one. So when light in the form of photon passes through the solution, some of it gets absorbed by the molecules in the liquid. So Beer-Lambert's law is like a guide that tells us how much light gets absorbed and help us figure out the concentration of the substances in the solution. So the cool thing about the Beer-Lambert's law is that it establishes a linear relationship between the absorbance and concentration. So by measuring how much light or absorbance is being absorbed, we can determine the concentration of the solution. So here the equation relates as the absorbance equals to A times B times C, where A is the analyte's absorptivity, B is the path length, and C is the analyte's concentration. To better understand, the Beer-Lambert's law equation could actually be rewritten as this one. So absorbance is equal to epsilon times B times C, where E is actually the molar absorptivity of the solution in the sample. So next, what are the limitations of the Beer-Lambert's law? So number one is fundamental limitation. At higher concentration, the individual particles of analyte are no longer independent of each other. So meaning higher intermolecular forces of attraction affects the absorbance of the data, which could ultimately affect the linearity of our equation. So next is chemical limitation. So deviation might occur if the analyte is involved in an equilibrium reaction. So as we recall, in the equilibrium reaction, there happens to be a forward or reverse reaction that could fluctuate the concentration of our analyte. And since our analyte's concentration is directly related to absorbance, huge errors might happen when we try to graph the data of our reading. So next is instrumental limitation. So stray radiation are imperfections in the wavelength selector that allow light to enter the instrument to reach the detector without passing through the sample. So I want you to imagine that when a window or a light from a window shines through the instrument, certain wavelength could actually go through the instrument, affecting the reading of our sample. So this could actually be prevented if we could place the instrument in a well-contained area or controlled area to prevent certain stray radiation from happening. So next is non-polychromatic radiation. So even the best wavelength selector passes radiation with a small but finite effective bandwidth. So there is no such thing as perfect wavelength selector. So since light or a photon exists in the spectrum, there are certain errors that could not be prevented in such a way that since photons could. So Beer-Lambert's law actually states that monochromatic light should exist as a single wavelength. However, since this is not a perfect world, certain radiation could ultimately affect the reading of our sample. But this could be further prevented by improving the laboratory practices. Is the multi-component analysis. So if there are no interaction between the components, then their individual absorbances are additive. So for a two-component mixture of analyte X and Y, their total absorbance is computed from the equation below. So how do we know the individual absorbances of each analytes? So we do this by making a standard solution or a solution with a known concentration and reading its absorptivity. So by doing that, we could use the Beer-Lambert's law to determine the molar absorptivity of that sample. And then what we have to do is to plug in the molar absorptivity since it is actually the constant in the equation, and then we deduce each equation. Therefore, knowing the total absorbance or the individual concentration of each analyte. So that actually concludes the part of my report. Thank you and God bless.